In a previous lecture, we've defined the critical Mach number and the drag divergence Mach number. And in this lecture, we will see what happens for an aerofoil if it's in a transonic flow. Especially, we will pay attention to their CL and the CD variations and try to explain why we have those type of variations. And the analysis is taken from a CFD simulation. Okay, so let's see what happens to the aerofoil in a transonic flow. Okay, so this is a simulation result of the CL/CD variation across a Mach number between 0.3 and 1.2. And the aerofoil is a NACA 12 aerofoil, and the angle of attack is small, about 3 degrees. So it's 3 degrees in the angle of attack. And so the simulation was performed through ANSYS Fluent, and the details are not given, just an aerofoil. Maybe I can give later. So the Mach number range is from 0.3 to 1.2, and the blue curve is a lift coefficient, and the red curve is a drag coefficient. Actually, we've already seen the drag coefficient variation change in the previous lecture, but that was just a conceptual curve. I made it by myself. This is a more realistic one through actual simulation. And we can see there's a geometrical change in the CL, so it goes up first and then comes down and then goes up again and then comes down. So and also the trend is not synchronized with the drag coefficient. So let's see the explanation why we have those geometric change in by increase, especially in the transonic regime. Okay, so in order to do the analysis, we want to study the curves, the two curves in 5 regions. And you can see region 1, region 2, region 3, region 4, and region 5. And region 1 is between Mach number 0.3 and 0.7, and region 2 is 0.7 to 0.74. And region 3 is 0.74 to 0.86, and 4 is from 0.86 to 0.9, and then the rest of the region is beyond larger than 0.9. Okay, so let's see the reasons why in different regions. Yeah. Okay, so now let's start looking at region 1. Okay, let's first see region 1. Region 1, the Mach number is from 0.3 to 0.6. And I'm giving the Mach number contour in here. And for when a free stream Mach number is 0.6. And why I put this out, this is because this Mach number is actually the critical Mach number, because if we zoom in, we can find there's only tiny region over the aerofoil surface. It has Mach number 1.0. So we can define this is a critical Mach number. And you may wonder, how do we determine the critical Mach number in the simulation data? So what you can do is you can, for example, you can check maybe 0.5. You don't know if you don't know 0.6 at the beginning. So let's check 0.5, and we see we see the flow field, and then the Mach number over the surface is all below 1. Okay, so it's not. We gradually increase the Mach number, then we increase to 0.58, and we can see still it's all subsonic. And then we increase to 0.6. Okay, so at this point, we just notice maybe 1 grid or 2 grids, a tiny region has Mach number 1.0. So we can determine this is the critical Mach number. If we increase further, we will see the bubble or the finite region containing Mach number 1 larger than 1 will increase. So this definitely confirms and the critical Mach number is 0.6 in this case. Okay. And the other thing very important is to look at the CP. Why we want to look at the CP? Because the CP, the area wrapped by the the CP curves of the upper surface and lower surface is equivalent to the lift. Okay, so if we pay attention to the lower plot of the CP distribution, and if you look at the CP axis, namely the vertical axis, and you can see it's inverted. We have negative above and positive below, and this inversion is made to make the CP curve of the upper surface showing at the top and the lower surface showing at the bottom. Okay. And you may notice there a bit undulation. That's a numerical effect because maybe there's not enough grade at the beginning, close to the leading edge. That's how you get the undulations in the pressure distribution. I would say it's a numerical artifact. Now we move to region 2, which is a very narrow region, and Mach number is from 0.7 to 0.4. And I only have 3 simulation points. Let's see what happens. So in region 2, the Mach number is from 0.70 to 0.74, and the Mach number contours are shown here. And what kind of observation we can make? First of all, we have supersonic region, and the supersonic region is actually not very weak, and so the Mach number is the peak Mach number can reach about 1.2. And what else? And we can see there's a normal shock wave terminating the supersonic region, and also by increasing the Mach number, and the shock wave moves downstream. Right. So as I write in here, shock wave starts to form on the upper surface, and an abrupt increase of drag will be caused by the shock wave. So that's a wave, typically the wave drag. And that's why we get abrupt change in drag coefficient. And how about CF, the CL lift coefficient? And it's so we need to move to the CP distribution. Okay, so this is a CP distribution, pressure coefficient distribution, and we can see the lower surface. Very interesting. The distribution is barely changed. They almost overlap, only slight change, but on the top surface, the leading edge, the part from the leading edge is overlapped, but once you go to the shock wave, following the shock wave motion, and the curve moves, the hump area moves downstream over the surface. And as we know, the area wrapped by the CP curves from on the up and the lower surfaces indicates lift coefficient, lift. So you can see by increasing Mach number from 0.7 to 0.74, the area wrapped by the curves is increased. That explains why we get larger CL, or the CL increases in this region too. Okay, so you can see to examine the CP distribution is very important, and also the Mach number contour actual flow field visualization help us to understand, to have a clearer understanding about the flow field. Okay, so now we move to region 3, and the Mach number is increased from 0.74 to 0.86. Okay, so it's a slightly wider region than the region 2, than the previous region, but we can see the drag continues to increase, but there will be a sudden drop in the lift. Why? They have different or opposite trend. So let's see again. And so this is a Mach number contour again, and so I have 6 plots at different Mach numbers. So the first row, the Mach number increases from 0.76 to Mach 0.8, and the second row is from Mach 0.82 to Mach 0.86. And so what kind of observation we can have? So in the first row, before 0.8, we don't see any shock wave over the lower surface, but the shock wave on the top surface becomes stronger. And also the wake region or the low speed region behind the shock wave is growing. The size becomes larger. And in the bottom row, and we can see the development of the shock wave over the lower surface. Can you see that? And also, in the meantime, the low speed region or separation region becomes larger. And that's what actually happens in the flow field. And if we want to understand the CD increase, and this is perhaps because the increase of the low speed region of flow separation, that also contribute to the drag coefficient increase, dramatic increase. But if we want to understand why there is a drop in CL lift coefficient, we need to look at the CP distribution again. I think so. Based on the analysis on the Mach number contours, we can explain why there's a dramatic increase in CD, but it's not sufficient to understand the CL decrease. So let's move to CP plot. Okay, so this is CP distribution for region 3, and we can see one thing. And since let's first look at the top surface, and the arrow indicates a Mach number increase. When the Mach number increases, we can see that on the top surface, the shock wave is just a slightly downstream movement on the up surface. So we can say it's roughly the same. The blue curves slightly increase, but if we look at the lower surface CP, and there is a very big change because of the shock in production of shock wave on the lower surface, and we can see these red curves. When the Mach number becomes larger, it will have this region which is beyond the blue curve, and this extruded region will be contribute to negative lift. So in total, there will be a compensation effect from the blue part. So in total, as in whole, the total lift has a dramatic change, especially when the shock appears on the lower surface. Okay, so this explains why you have a dramatic drop in the lift coefficient. And in the previous slide, we understand why we get CP increase, CD increase. That's because of the separation appearance of the separation region. Okay, and now here is the zoom in view of the local flow field, a zoomed in view of the flow field at the shock foot, and we can see increasing the Mach number does make the separation bubble stronger and larger, especially in the first row, right? Okay, and this will contribute to the drag coefficient increase. Okay, so the next region, region 4, it's again a narrow region, but in this region, CL and CD both increase magnitudes. Okay, so let's see from 0.86 to 0.90. Okay, so by increasing the Mach number, we can find the lower surface flow field actually nearly stays the same, but the up surface shock wave will move downstream. It will move downstream, and we can see at 0.88 there is a low speed region, separation region after shock wave, but since the shock wave will move towards the trailing edge, the separation will be removed. There won't be any separation at the trailing edge. So this is a benefit for the drag, but and the drag will still increase, but with less trend or less gradient. Okay, so this is a visualization of the trailing edge separation. We can see when you increase the Mach number, free stream Mach number from 0.86 to 0.88, we can see the shock wave, up surface shock wave will move towards trailing edge, and then the separation area becomes smaller. And this will contribute to the reduced gradient of the CD. And if you want to explain why you have the CL change, again, we need to look at the CP distribution. So we can see the lower surface curves are hardly changed, but the top surface, because shockwave moves downstream, and there will be less negative contribution. So the CL will increase in region 4. So I hope it's clear to you. And then we move to the next region, and especially when the aircraft is flying beyond Mach 1. Okay, now we see column by column. So in region 5, the Mach number is from 0.92 to 1.2. And we can see on the left, very left row, and the Mach number increases from 0.92 to 0.94. And we don't actually see many changes, no significant change. And from 0.898 and a 1.0, and also there's a little change, and in 1.1 still quite similar to 1.0, but once the free stream Mach number is beyond 1, which indicates a supersonic flow, we will have oblique shockwaves from the leading edge. The bow shockwaves detached from the leading edge. So this is observation from the Mach number contours. And if we want to evaluate the CL change, we need to again see the CP plot. And it's not that obvious, but roughly it's give you an idea how the CL will change. Is that right? So the CL change is not as significant as the shockwave movement.